Okay, so I'm Mike Douglas, and this is the New Technologies in Mathematics seminar series. And today we're delighted to have Ivana Balažević and Carl Allen to speak about knowledge graph representation. So they'll take the talk in two parts. And as usual, if you have questions, I offer to read the chat, so you can put a question in the chat, and I can answer it, or I can ask the speakers, and then at the end of each part, we'll stop for general questions. So with no further ado, please start, Ivana and Carl.
Yeah, thanks very much. Thanks for inviting us to give this talk. Hello, everyone. So we're Ivana and Carl. We're just about to finish our PhD at the University of Edinburgh. And what we're going to talk about here today is our work on knowledge graph representation, which are several papers that we published during our PhD. And so this talk is going to be in two parts, as Michael already said. So first, I'm going to give a bit of intro into like knowledge graphs and knowledge graph representation, and then talk about some of our recent knowledge graph embedding models. And then Carl's going to talk about a bit more theoretical part of this work, about our theory on how is the semantics encoded in the geometry of these learned embeddings. Oopsie, sorry. So, okay, so just in general, so first of all, like I'm pretty sure most of you already know this, but just in case some people are not familiar with knowledge graphs. So yeah, what are knowledge graphs? So knowledge graphs or knowledge bases, they're the same thing, and they're these large collections of facts that are typically represented in the form of triples. So typically, can you see my cursor?
We can.
Yeah, okay, great. So yeah, typically we have these triples, which are binary relations between entities. So in this example, we have a subject entity A, object entity B, and a relation between them, father of. So these knowledge graphs contain many, many triples. And then these, when you look at them like in a different way, you can think of them as a graph, which is this representation here. So entities in this case are nodes in the graph. So here A, B, C, and D. And relations are these type-directed edges between them. There's many types of relations typically in a knowledge graph. So they can be symmetric, for example, like this relation married to. So A is married to C, and C is also married to A. They can be asymmetric, for example, the father of relation. So A is the father of B, but B is not the father of A. And they can have various other types of properties. So for example, transitivity or hierarchy. Another way to think about this, and this is going to maybe come in later when I talk about one of our models, another way to think about a knowledge graph is, so for a normal sort of graph, you have an adjacency matrix of like which node is connected to which. And given here we have like types of relations, we're going to have an adjacency matrix for each relation. So we're going to have effectively like an adjacency tensor. So this big binary tensor of triples, which says which entity is connected to which under a particular relation. So that's just another way to look at this. So why are knowledge graphs useful? So you can do various things with them. You can do question answering, fact checking, information retrieval, or what is of particular interest to us is link prediction, which is based on some facts that already exist in a knowledge graph. We want to predict what other facts are true. So this is particularly interesting because knowledge graphs are generally very incomplete because they have been typically created by humans, and it's just impossible to cover all possible true facts. So yeah, here in this example, so we would maybe want to, from knowing that A and C are married to each other and that A is the father of B, we would like to predict, like to be able to predict that C is the mother of B. Okay, so in order to be able to predict these new facts from the ones that we already know, we need to have a way to somehow mathematically represent these entities and relations. So what's typically done in the knowledge graph embedding literature is to represent subject and object entities as vectors in d-dimensional space, which is typically of the order of a couple of hundreds. And then relations are represented as transformations on these vectors. So we have here FR, which would be a the transformation that is specific to the subject entity embedding, and GR that is specific to the object entity embedding. And then once we've applied these transformations on the entity embeddings, we define some kind of proximity measure to measure how, in a sense, close these two relation transformed subject and object entity embeddings are. And that can be something like Euclidean distance or dot product. So just to kind of make this maybe a bit more clear, just a little example here. So if the subject entity embedding is Edinburgh and the object entity embedding is Scotland, and the relation is capital of, we apply like relation-specific transformations specific to the relation capital of, like FR and GR, to then obtain these relation transformed entity embeddings, and then we check whether they're close under the proximity measure that we have defined. And what kind of brings together all of these things that I've talked about so far, so the entity representation, relation representation, and proximity measure, is what we call a score function. So a score function is what is used to predict whether a particular triple is true or false. We learn these representation parameters, or like we optimize them to improve the prediction accuracy, so that if two entities are related under a particular relation, a score function gives a high score, and if they're not, so that it gives a low score. And then another thing that's typically done is that we apply a nonlinearity, such as, for example, logistic sigmoid on this score, so that we obtain something that's like a proxy to a probability of a particular triple being true. So from all the things I mentioned so far, what kind of differentiates different models? So typically entities are almost always represented as vectors in most models that we've seen so far, but what differentiates the models is the type of relation representation, which can be additive, multiplicative, or both of these. And the proximity measure that is used, and as I already mentioned in the previous slide, that's typically dot product or Euclidean distance. So I've here put all of the different types of the relation representation that I mentioned, and also an example of each of the score functions of each particular type, and some models that correspond to a particular score function. So the models that I'm going to talk about are two of the earlier, like more notable models, and two of our latest, two of our models from like about a year and a half ago now. So first off, with the multiplicative score function. So to just kind of put it in the context of what I've just said about like this categorization of score functions. So for multiplicative models, they like obviously use the multiplicative type of relation representation, and for a proximity measure, they typically use a dot product. So here, this example, so we have the subject entity embedding, object entity embedding, and a relation specific matrix. So which can be applied either on the subject or the object entity embedding. And then we measure a dot product between this relation transform subject, in this case, in this example, and the object entity embedding to obtain the score. So yeah, the two example models for that are Dismalt, which is a really simple model and one of the early ones, where the matrix WR in the middle is diagonal. which immediately means that this mult cannot model asymmetric relations, because the score is going to be the same whether we swap the order of subject and object entity embedding or not. Tucker is our model from EMNLP from 2019, which I'm going to talk a bit more about on the next slide. Okay, so those are multiplicative models. From additive models, like maybe the most like representative one is TransZ, which is again one of the first models. And TransZ uses like this vector addition as a relation representation type, and squared Euclidean distance as a proximity measure. So we just translate the subject entity embedding and measure the Euclidean distance between the translated subject and the object. So those are the additive models. And then there are models that combine both the additive and multiplicative components. So here we have one of these models is Mirror, which I'm again going to talk about in a couple of slides. But yeah, so like what the score function in general looks like is we have multiplicative components, which are these matrices here applied on the entity embeddings, and we have some additive components. And yeah, the proximity measure is typically Euclidean distance in this case. And these are some subject and object specific biases. Okay, so I'm just going to go into a bit more detail about the Tucker model. So Tucker is based on the Tucker decomposition of this binary tensor representation that I was telling you about in the beginning. So if you think of this whole knowledge graph as being this large binary tensor of like, yeah, ones if two entities are related under a particular relation and zero otherwise, then subject to this like nonlinearity, we can decompose it into this core tensor here, which is much smaller. And the three matrices for the entity embeddings, two for the entity embeddings and one for the relation embeddings. So here you can see this would be a score visualization of the score function for one particular triple. So we have in green the entity embeddings for the subject and object entity, and then we have the relation embedding for the relation. And then we have this entity and relation agnostic core tensor in the middle. So once we multiply this core tensor with this relation specific vector, we obtain a relation specific matrix, like here on the right, which is the same formula that we've seen before for multiplicative models. I also have it down here. So just like the entities multiplied by a matrix between them. So why would we even want to do that? Why do we even want to have this core tensor? Why don't we just immediately start with what we have here on the right? And this is actually an existing model called ResCal. So the reason, there are like two main reasons. The first one is multitask learning, which given that like this this tensor in the middle, core tensor, is relation agnostic, we can think of it kind of as containing a shared pool of prototype relation matrices, which then get linearly combined using the parameters in the relation embedding, this small WR. So, and then to obtain this relation specific matrix, large WR. And this is going to be particularly important for knowledge graphs that contain a large number of relations, and in some cases, not a lot of data per relation, which means then that their relation representation has a chance of being learned from whatever is known in this like core tensor from like the other relations. The other point why we want to do this rather than just immediately like defining it like this, like ResCal on the right, is because in this case, we have a quadratic growth of the number of parameters with the number of relations. But in the case of Tucker, the number of parameters with the number of relations and entities grows linearly because this core tensor is independent of the number of entities and relations. Okay, so this is Tucker. the second model that I wanted to talk about is MUIR, which is our paper from NeurIPS 2019, and MUIR kind of, so this paper, the main focus of the paper is on hyperbolic embeddings of hierarchical knowledge graphs. And MUIR was kind of created as a byproduct, mostly as a byproduct, as in like a Euclidean equivalent of the hyperbolic model. But then it kind of performed really well. So Carl's going to talk a bit more about MUIR in the theoretical part of the talk. So the score function of MUIR is this, what I have on the bottom of the slide. So we have a multiplicative component, so a matrix that is applied on the subject entity embedding, and we have an additive component applied on the object entity embedding. And then we measure this negative squared Euclidean distance between the two, and we add some subject and object specific biases. The visualization just kind of maybe helps to think about this, or like another way to interpret this. So you can think of entity embeddings as being in the centers of these spheres, and the radiuses of the spheres are defined by the biases. And then what these relation-specific parameters, big R and little r, do is they move these spheres around in space, so that if two entities are related in their particular relation, they're going to end up overlapping. And if they're not going to overlap. So this is just another way to kind of visualize this score function, and just maybe makes it a bit clearer. Okay, so just to recap this part. So yeah, I've introduced knowledge graphs as these collections of binary relations between entities. And they are useful for like various different reasons, like question answering, fact checking, link prediction, and so on. And but to be able to predict any new facts or kind of reason with them, we need some kind of representation. So we typically represent entities by vectors or embeddings, and relations by transformations from the subject to the object entity. And then we need this proximity measure between them. So there's been like, I've only introduced like 4 models, but there's been many models in the knowledge graph embedding it or like link prediction literature, and they've been getting more and more accurate, but we're not like still not really sure how any of these work, or then like not sure how to improve them. So yeah, I'm gonna leave it to Carl now to talk a bit more about like our theory on how is this semantic information encoded in the geometry of the embeddings. Okay, let me just stop this sharing.
Okay, thanks. Are there questions for Ivana at this point? If not, we can continue.
And we can't hear you, Carl, I think.
Yeah.
I don't know if you're talking.
You're muted, Carl.
Right, sorry, can you hear me now?
Yes.
Okay.
Yes.
Yeah. Right. Sorry about that. So yeah, thanks, Ivana, and thanks for inviting us for the talk. So I'll just now try and explain our more recent sort of theoretical explanation for kind of how the semantic things like words and relations end up being more numerical objects like vectors and transformations. And doing this, it's kind of not really immediately obvious where to even start, given they're not obviously very mathematical words and these relations. So we just started by simplifying, and rather than considering word, relation, word, as we have in knowledge graphs, we just drop the relation and just consider how words can be represented. And this is kind of quite an established field in natural language processing. Plenty of word embedding models out there, and latest language models are extremely complex and give contextual word embeddings. But what we're looking at here is just kind of classic one word has one vector kind of embedding models. And two well-known ones there are Word2Vec and Glove from a few years ago now, where they both work similarly in that they'll train on a large body of text, large corpus, and every time a certain target word appears, they'll be trained to predict the context words that appear around. So for every word in the dictionary on both sides, there are these two matrices in between. And you can think of within those matrices, there's sort of one row or like a vector corresponding to each word, both as a target word and a context word. And those are what comes out as the embeddings. Excuse me, sorry. So, okay, why start here? Well, it seems a promising place to start because it's well observed that semantic relations between words manifest as geometric relationships between these word embeddings. And that's kind of what we're looking for in knowledge graphs. In particular, very almost trivially, similar words have very close embeddings, and more interestingly, perhaps, analogies often are sort of known to exhibit this kind of parallelogram structure. So an analogy is this like a common relationship between word pairs, like man is to king as woman is to queen. And it doesn't always seem to be the case. There's kind of like people quibble over this, but there's definitely some structure there. So that often, if say you didn't know the answer, you could say what man is to king as woman is to what, by essentially taking the word embedding for king, subtracting that for man, adding that for woman to sort of move around this parallelogram, and then often find that the closest word embedding to this point is the answer to the analogy. So these are two kind of just well-known things for word embeddings, and the aim is to try and take this kind of understanding into knowledge graphs. So first of all, we try and understand, well, where does this structure come from? And you can consider the loss function of Word2Vec, and in particular, its gradient, set that to 0, and you get this kind of well-known result that the loss function is minimized if the target word embedding of one word I and the context word embedding of word J dot product to give this value here pointwise mutual information, which is a kind of well-known quantity from information theory and crops up throughout the history of natural language processing. And so when this cropped up, people were kind of pleased with this result, but it doesn't really in itself explain anything much more. Like, it doesn't explain those previous findings, like, obviously. Further, it doesn't actually hold either. This is not an equal. This is not an equality, because this PMI, this essentially means that the matrices W and C factorize this matrix of PMI values, and this matrix of PMI values is massive. The dimensions are the number of words by the number of words, which is in the order of millions typically, whereas the dimensionality of these embeddings is typically of the order of hundreds. And so for this to be equal, you'd require the PMI matrix to be extremely low rank. In practice, that's not really the case, and so this is more approximate, i.e. word embeddings are really projection of the embedding WI can be thought of as a low rank projection of a row of the PMI matrix, corresponding row of the PMI matrix. But this is useful still though, because where we have word embeddings, we don't know what the parameters, the numbers in those vectors, we don't know what they mean. But if we can consider them as low rank projections of these values, then these have an explicit mathematical form, so we do know what these mean. So PMI means that this probably means it's a comparison of probability. So if if word J is more likely to appear in the presence of word I than it would ordinarily, then this is a positive value. If it's less likely to appear, it's negative, and these two words are independent, it's 0. So this has kind of got that semantic meaning, it's got meaning. And if we can find structure between rows of the PMI matrix, then that's probably then the reason why there's structure found in the low rank projection in word embeddings. And because we've got an explicit mathematical form for these PMI vectors, these rows of the PMI matrix, then we can consider that. So yeah, so this is just saying then, so we now consider PMI vectors. So for every word, we consider its full row of the PMI matrix. So its interactions with every word in the dictionary. And so each component of the vector has this form, and so it considers whether for each word that word is made more likely or less likely in the presence of the target ith word. And just as probability vectors of a multinomial distribution sum to 1 and therefore they lie on a simplex, similarly vectors of this form can be shown to lie on some kind of like surface in this very high dimensional space. So we can now consider explicit interactions between PMI vectors. So similarity, yeah, and we're trying to relate these interactions between PMI vectors to actual semantic meaning. So similarity is just where words are similar, i.e. kind of synonymous. They're more or less interchangeable within text, and therefore you'd expect the distribution of words found around them to be broadly the same. And this is identified simply by taking the difference between PMI vectors. So this amounts to a log ratio of the distributions of words found around word I and word J. So if these distributions are similar element-wise, then these components will be 1 and the log will be 0, and this difference will be small, i.e. these two PMI vectors will be broadly equivalent. So we have the property similar words have similar PMI vectors, and therefore also their low rank projection, i.e. word embeddings. And it's just a sort of schematic. So where distributions are similar, the PMI vectors corresponding to those are similar. We can move on to paraphrases. So this is a semantic relationship where a set of words has a similar aggregate meaning to another set of words. So for example, man and royal together semantically mean a similar thing to king. So by similar, if they have a similar meaning, we expect then overall the distribution of words appearing around them to be similar. That's kind of what we mean by sort of similar, semantically similar. They have the same sort of effect within text. And when we add two PMI vectors, originally we get this form, which isn't much use, but if we compare, if we bring in the PMI vector of any other word, then terms can be arranged into this format, which looks a bit of a mess, but we can immediately just ignore these terms here because what we're wanting to do here is say, if we add two PMI vectors, when is that similar to the PMI vector of another word? And these two terms have nothing to do with the other word. WK doesn't appear in here. They're only to do with the independence of these two words on the left here. So long as these are sufficiently independent, we can ignore these terms. So the only thing that matters then is this term here. And so we can notice that, again, this is a ratio of distributions over all words. One distribution in the presence of WI and WJ appearing together, and the other is the distribution of all words in the presence of word K. So if these two distributions are similar, i.e. these I and J appearing together has a similar semantic effect. They create the same sort of distribution or disturbance in the distribution as each other, then this term will become small, and i.e. all these error terms are small, and this simple relationship will then appear to hold. So this identity is true for any 3 words you can think of. It's true, but only for certain words will these terms become small, and this then relationship sort of like come out. Otherwise, it would just be obscured by the error terms. And so similarly, when we project down into low dimensions, the same sort of structure will appear between word embeddings. Certain word embeddings will appear to add to other ones, and some will not. They'll just give gibberish because these terms will obscure things. And there's just a little diagram I think we kind of covered. So finally, then, sort of these kind of overarching categories of semantic relationship that we can consider between word embeddings is back to analogies. So again, where word pairs share a similar semantic difference, man to king, woman to queen, we could extend this boy to prince, girl to princess, maybe house to castle, even, right? The same sort of semantic notion of difference. And for all the reasons we've seen before, we can show that this relationship here will hold between PMI vectors explicitly when certain distributions are equivalent, which then makes sense in terms semantically, as we've seen before. So the semantic relationship creates similar distributions, and those distributions mean that error terms will become smaller, and this relationship will kind of come out. And this explains then why we see this analogy template in word embeddings. So what I've explained so far is then the subject of a couple of papers that essentially explain why there are geometric relationships between word embeddings that relate to semantic relationships. And now the idea is to take that to knowledge graphs. So first, we just changed the picture slightly. So this is the familiar picture for analogies, and we'll just change this so that we can consider it for more broadly for knowledge graphs. So what we're saying here is that we're just representing the PMI vector slightly different. Here it's just a point in space. Here we draw it out kind of more explicitly. So each like rectangle here represents some like a cartoon of the PMI vector, and the blue and green blobs represent say high word association, so positive PMI values, for example. So for this to hold, what we really require is that the PMI vectors are between man and king are broadly the same. For the most part are the same. We don't really care what's in there, but they just have to be the same. And then there's this specific difference, this specific, if you like, additive difference. And then for woman and queen, again, most of the vector, which we don't care about, just has to be the same. And so that the only difference then is this specific difference, and that specific difference is the same as this specific difference, i.e. that green blob is this green offset here. Right, that's this is some vector component, and it's equivalent to this vector offset we're seeing here. And so this these two pictures represent the same thing, but what we've done is kind of split this the analogy as talked about in word embeddings. We want to now get to the language of knowledge graphs and kind of see this as just binary relation between words, a common binary relation between words. And so this is a kind of important realization that really analogies, as I talked about as this catch-all term in word embeddings, is really kind of very sort of synonymous with the catch-all term of relation in knowledge graphs. And just in the same way, both of them are used so broadly, it kind of masks the fact that not all analogies are equivalent and not all relations are equivalent. You've got lots of different types of relation. Like Ivana said, there's symmetric ones, asymmetric, transitive, hierarchical, you name it. And so they're, you know, to try and just treat them all identically is like to say all maths problems are the same. It's just kind of ludicrous. So what we're trying to get at is understand what these differences are, and how you can kind of represent different classes of relation. So what we're looking at here, we call a specialization. So man to king you know, king is a special version of man. It's still a man, and it's a contextualized version of a man. And in a way, you can sort of see that as like adding context. And similarly, we take woman and we add some kind of context, and we get to queen. But not all analogies fit that kind of semantic template. But in this special case, we can see that that relation in a knowledge graph could be represented simply by adding a vector, as in the trans-E model. As I said, not all relations fit this shape. And so that adding a vector is not going to be appropriate in all cases, just as it's not appropriate for identifying all analogies between words. But this general notion and this general picture of how things work kind of gives us a foothold for considering other types of relations. So that's what we do now. So here we're just trying to classify and sort of get a handle on how the PMI vectors of related words kind of relate to each other under different types of relation. So we've seen, like, very simply under similarity, they just have to be broadly the same. I.e., you know, and just in previous wording, i.e., both words induce the same kind of distribution on words around them, right? So that's what this all has like a real mathematical meaning. We're just cartoonifying it just so we can sort of like get a simple kind of idea. A kind of cut down version, a weakened version of similarity is relatedness, where rather than all kind of components having to be the same, just a certain set of word components have to be the same. You know, like a common theme. So milk and cheese, they're not identical words, but they're related. So some words will co-occur with them in a similar way, and other words won't. But certain ones will, and they're the ones maybe you're interested in, to say that word is related to that word in a particular way. And there are different ways in which things can be related. You could have a different subset of words, but this is a sort of a watered down version of similarity, or if you like, the other way around. If this box were made bigger, you get back to similarity. Specialization is what we've seen already, where essentially, for the most part, there's relatedness, i.e. the vectors are the PMI vectors, the word associations are similar, apart from a very specific required difference that defines the relation. But just as you could consider this as adding a context, or going the other, you could go the other way and say we subtract the context, go from man to king or king to man. So really, whether you add it or subtract it is just two sides of the same coin. And so you can sort of generalize that and say, well, maybe we want to subtract something and add something. So instead of going from man to king, you could say go from boy to king, because we subtract youth and add royal at the same time. So these, you know, it just sort of generalizes the picture slightly. And you can see this kind of hierarchical build-up of structure, because you know, if we, you know, this is a special case of this if we set this to 0. Relatedness is a special case of specialization if we set this to 0. So there's a kind of, you know, subsumption kind of hierarchy building up to these. And the last kind of step is to recognize that these two relations are essentially one-to-one. So if we have man and we add royal, we get king. I mean, up to synonyms or something, like just fully interchangeable words. These are kind of one-to-one. Woman goes to queen. But not all relations are one-to-one. So for example, you'll find relations like America is to apple pie, like the UK is to the London bus. You know, just something iconic, and it's not one-to-one. It could be, you could pick a load of different other words to fit in the sort of second word place there. You know, America is to many other things, and so in terms of this picture, that means that these sort of green blobs have to be there, but they might not be fully specified. They might be they might come from a subset of allowed kind of contextual options. And so that would mean that you can then have many-to-one, one-to-many type relations. And we apply this kind of categorization to the actual relations found in knowledge graphs, and are able to sort of classify. So here this is an example of WordNet 18RR, sort of common knowledge graph used to evaluate representation models. And we can just by eye sort of classify what different relations, how different relations fall under this categorization. And it might seem a bit ad hoc, so we've considered, how complete is this? Like, does this cover all possible relations? And this isn't a proof, but we can sort of, if you like, mathematize it a little by, if we consider these PMI vectors as sets of features, we can consider these relations in terms of sort of set operations. So similarity requires set equality, relatedness requires some subset equality, context shift requires some specific set difference. And from the perspective then of each feature within this set of word features, under each relation, it must necessarily remain unchanged, i.e. in the relatedness box. It must necessarily change or potentially change if it's in this context shift box. Otherwise, it's irrelevant. And so there's this sort of positive, negative, and zero type quality to each feature under each relation. And we conjecture that that essentially does classify all the kind of semantic relations you would find. So we think that does actually describe all possible semantic relations. There are, you could magic up other types of relation, like more syntactic kind of relations, like cat is to cot as bat is to bot, but they're not semantic, right? It's just down to spelling. So the whole thing about creating similar disturbances in the distribution of words wouldn't hold. It's all down. It has to be a sort of semantic relation. So just to summarize so far, then we're saying that if entities of knowledge graphs were represented by PMI embeddings or some low rank projection of them, then we've got this kind of idea of how this cartoon-like picture almost of how the two representations will relate to each other under different categories of relation. And so if we know what this difference should look like, we could then design the transformation from subject entity to object entity to sort of capture that, to identify it. So if we need to, if a certain area or component of a vector should be the same, well, we can test for that by projecting both vectors onto that subspace under some projection matrix. And so we can see that multiplication under this projection matrix would be required. Similarly, where there's these other relations, the specialization and context shift relations, where we see this part needs to be added, we can just do that, right? We just add some vector, and maybe we need to do a bit of both. And so project, and also once projected down onto some subspace where where we have to check there's this component of similarity, we can then also add in some difference that we need to observe for the relation to hold. And so based on this, so based on this kind of perspective from PMI embeddings and word embeddings, we can say what under those conditions, what the relation representation would need to look like to identify the relations, to map from the subject embedding through to the object embedding. And we notice in particular that what we end up with in the sort of in this case here is very similar to the mere loss function, combining both multiplicative and additive components. So it's then able, because we have this hierarchy to the types of relation that we've seen. So relatedness is kind of subsumed by specialization, which is subsumed by context shift. If the function can accommodate context shifts, then it can accommodate all the rest anyway. So this loss function that you can can get to by sort of just stepping through this mirrors Mir, and therefore it makes sense then that Mir can represent all these different types of relation under the assumption that embeddings are represented. Words are represented by these PMI embeddings or projections thereof. So where we've got to then is with from sort of first principles, from just considering word current statistics, we're able to derive these like geometric properties of relation representations. And further, the components of them, the subspace you project down onto the component you maybe add to get from, say, man to king, they have semantic meaning. It might be that, it might be hard to sort of say, to relate that to another word in the knowledge base, because knowledge bases don't have many words in them. But nevertheless, there's some kind of notion within the space of this kind of meaning. And finally, we don't present tables and things here, but this is all empirically supported. So what we're presenting is essentially a way to represent entities and the relations between them that would work. And then what we compare is we compare existing knowledge graph representation models to that. So what we work out theoretically is you require multiplication for this projection of finding similarity. We need to add bits, and where we then contrast that against actual knowledge graph representation models, some of which have multiplicative bits, some have additive bits, some have both. And what we find is, and what we show in the paper, is that the more that a knowledge graph representation model is able to fit what we show it needs to do to represent the relations, the better it performs on a relation by relation basis on different types. So if we expect it to be able to represent this type of relation, we find this kind of corroboration between what we expect and what we see in practice. So in particular, this main finding that or explanation as to why Mir outperforms previous kind of approaches, which tended to be down one avenue or the other. It sounds almost obvious to say, well, I just do both. But I mean, these things are obviously in hindsight sort of thing. And the other thing is that really it's not a retrospective explanation, because really we came up with Mir based on kind of early intuition from this, and then kind of, if you like, retrospectively fleshed that out into a bit more of a sort of concrete kind of theory. And that's pretty much it. So this is now work that's due to appear in ICLR later in the year. And that's it. Thanks.
Okay. Thanks, Carl, Ivana. Do we have questions from the audience? Omri, did you? I mean, I have a question. If I mean, it's a very interesting picture, the types of relations, this semantic categorization, matching up with the type of embedding structure required to represent them. And then, as you say, you look at results for different relation types, and you get a correlation between performance as function of relation type and features of the model. Do you have any? So of course, all the model gets to look at in the case of the knowledge graph is the graph. I mean, is there some way of saying within the graph, what is it about the graph that makes a relation R, S, or C?
Yeah, I think that's kind of an interesting question, because you can sort of say this is cheating, because if you like, if you were just given a bag of relations and you say that's all you have, and you know nothing more, then I think actually no, I think there's only so much you can actually do with that in a way. Depends how complete that data is, if you like. Because I mean, what we're facing here with knowledge graphs is that you've got a bunch of you've got a bunch of relations and you're trying to predict some other ones. And I don't know, some of the ones that you're trying to predict may be somehow logically inferable from the ones in the training set, but I think a lot of them, I don't know, I think, I don't think they're all just, I don't think it's all just like, I don't think your test triples are all kind of in the logical span of your training ones. I don't think you can just infer them somehow with no outside kind of knowledge of it.
Well, I mean, clearly the only thing the model gets to look at is the graph. So it is all somehow encoded there in the graph. And certainly like the most simple cases like subrelation, if one thing is a subrelation of another, that's very obviously present in the graph. And maybe these more complex characteristics you develop, maybe they do have graphical descriptions.
Yeah, I don't really know. So if you just had, if you have this essentially the tensor, if you think of it as this binary tensor, and you have some ones and some zeros and then a whole lot of spaces, you kind of need to assume some sort of model in some way for inferring those gaps. And
I think a big challenge is probably that like that graph is so incomplete that, that I think there might be parts missing. So it might not even be immediately possible to infer that something is a subrelation of something.
It might be ill-defined. There might be too many potential, potential sort of, I don't know, like some rule that would be, which would explain it. There may be lots of rules that might explain what you're seeing. And it's almost like active learning. Maybe if you could fill one in, it would kind of rule out a lot of hypotheses and limit that. But it depends. It would be very much depends on what nature throws at you as to kind of, how much can be inferred from what you're seeing, or how many potential hypotheses there are, or do you come in with a heavy prior over those hypotheses to effectively, really cut that down already? And I think that's kind of what this is doing. It's kind of like saying with some external prior information, you can kind of like, it's a bit like snap to grid. You kind of like, rather than consider all of these potential things, we kind of like, clamp down to sort of, I don't know, some kind of half-baked structure in the first place. And I think if you were just given like essentially an arbitrary, obviously you're not given, it's not arbitrary, but to know what choice of structure lies beneath of these. If you knew nothing else, there might be lots of plausible structures, substructures that explain the bits that you see. But no, it's a really interesting question. I mean, there's obviously there's some mathematical answer to the domain of plausible explanations or something. But
okay, let me throw out another related question, which is that you started, of course. I mean, your main topic is knowledge graphs, but then there are also word embeddings, which are not in themselves related to knowledge graphs. They're related to co-occurrence statistics. And then, of course, the intuition you get from those could be applied to knowledge graphs. And I wonder if you've thought about the more direct connections. And the basic example of that is, at least that I know, is this deep walk embedding, where you actually take a word or point at a vertex in the graph, and you just start doing the random walk on the graph, and then you look at the set of vertices that your random walk generates, and you look at the co-occurrence statistics of those, and that's a reasonable embedding algorithm. So there is at least that one very specific relation between co-occurrence statistics and graphs. I wonder if you looked into that.
I mean, here we're essentially using that word-to-vec type algorithm on a separate graph. The graph that you get when you just consider all words as nodes, and then the graph of some text that sort of takes this random walk between them, if you like. And you take then snippets of that random walk, and that's what Word2Vec is then trained on. So we're sort of doing that, but then with a separate graph. I don't know to what extent. Yeah, I don't know to what extent. I'm sure someone's run that on knowledge graphs. We haven't.
Well, I think the deep walk is a pretty established thing. It's a few years old, but that was graphs without relation types.
Yeah. Sorry, that's on. I just mean that's on general graphs, I think, right?
Yeah.
Yeah. So I'm just not sure if that's been applied to knowledge graph itself.
Yeah, I can't think of me. Again, there's so many papers in this field.
Probably. Yeah, exactly. I agree. Can't keep up.
Yeah.
So,
okay. Yeah. More questions from the audience, or?
Just wondering about so your methods suggest some way of explainable, I guess, embeddings, because you have like clearly defined building blocks, and then giving these building blocks you can explain why something is learned, I guess. So yeah, I wonder what can be said about this. I mean, maybe it requires better data than we currently have, but I'm wondering whether. So the current knowledge graphs are probably not. For example, this WN19 is and many others. So maybe the data is not good enough for doing explainable embeddings. But yes, I'm wondering whether you thought about this direction.
Well, we are looking at so this model kind of unifies, if you like, word embeddings and knowledge graphs. And so one of the things here is even if you could say work out that a relation requires a matrix and a vector, and the vector has some kind of maybe some semantic meaning that we might attach to it, but if there's no word, if that word doesn't exist in the knowledge graph, there'd be no way to sort of like, if you like, check that it's close by and give it a label. Whereas if you could embed like these knowledge graph and entity embeddings within, unify them properly with Word2Vec embeddings, and then you'll have kind of embeddings for them, many other words, maybe some of them which don't even exist in the knowledge graph, but they'll be kind of all in the same kind of space, semantic space, if you like, with all these other words that then mean you effectively you've got more words to play with, more words that you could use to maybe try and describe. So like a vector offset within a relation might then correspond to a word vector that you have at the same time. So if you bring it all together, you've got more ways of like describing the space, and maybe you can attribute more, pull out more semantic meaning. You can assign a label to the semantics of like the vector offset or something.
Can I just add to that, like in terms of like data, we've looked at a few of these knowledge graph data sets when working on this kind of interpretability work. And yeah, we generally found like WordNet not to be too bad because it mostly contains relations between words, like where the two words are similar. So it is type of words that would appear in text or like in a lot of text, so that you would also, like if you would do Word2Vec on a text, you would probably have like a decent statistics for those words. But for example, we looked at freebase as well, and freebase is very different. And there you have mostly some sort of, I don't know, relations between people, who was married to who, and things like that. So it wasn't very useful. What do you say?
It's like gossip and tabloid stuff, like Leonardo DiCaprio did this and that.
Yeah, so it's not very useful for any kind of like not learning much from it, or like any kind of interpretability, but at least we found that.
It's more like ad hoc facts that you can't necessarily infer. Some you can, but like some of it seems a bit sort of, if you hadn't watched the film you wouldn't know, and so it's hard to necessarily just infer from the knowledge base. So there's less logical kind of relations and things going on. But I think that maybe gets to your point earlier, Michael, like on, what can you do if you're just given a bag of facts? I think it really depends there. And we, as Ivana said, we've seen it between these, you get very different results sometimes on Freebase and WordNet. And I think it's because they're very different. There's a very different flavor to the data.
Right. Okay, more questions from the audience? Okay, well, let's thank Carl and Ivana for a very interesting and stimulating talk. I will clap for everyone. And then we'll have a more private discussion following this. Let me